Hello students, how are you? I hope you are doing good. So we are here with the continuation of our revision series, and today we are going to revise the properties of solid and liquid rest. We have covered it into 2 days. In the previous lecture we have did with elastic properties of materials, and today specifically we are focusing on the properties of liquids. Okay. So today's topic that we are going to cover: streamline and turbulent flow, equation of continuity, Bernoulli's principle, speed of efflux and Torricelli's law, Archimedes' principle, viscosity and Stokes' law, surface tension and surface energy, then excess pressure in drops and bubble, and mostly the formula we will see, and then capillary rise. So this is all we are going to cover for today. Although we are going to see some PYQs also based on these topics. So let's get started with it. So firstly, if I talk about streamline and turbulent flow, so streamline flow is a steady flow also. It is defined as, it is also termed as steady flow or laminar flow or smooth flow. So in streamline flow is defined as such that if a particle, the fluid particles is moving in such a way, like these are the fluid particles that are moving. So if I consider a point here, let's say point A, so all the particle who's crossing this point A has the same velocity as its predecessor, which means if I taken two particle here, this is particle 1, this is particle 2. So when this particle reach this point A, let's say it has a velocity of 10 meter per second. Now, if this flow is streamlined, this if particle 2 is crossing this point in the same manner, so it will also have the velocity 10 meter per second. So that flow is defined as streamline flow, in which all the particle moves in a smooth flow, and the direction of flow is given by the tangent to that curve. Okay, so these are imaginary lines. First of all, streamlines are imaginary lines. If you draw the tangent to that particular point, you will get the velocity of flow at that point, and this velocity is followed by all the particle who is crossing this point. So that flow is termed as the streamline flow. Okay, in opposite to that, turbulent flow is not a smooth flow, irregular flow. Okay, in steady flow, how do we achieve steady flow? So generally it achieved at slow speed of the liquid, but when liquid travels with a very high speed, that flow will not anymore the laminar flow or streamline flow, it will become turbulent flow. Okay. So it is for slow speed, and turbulent flow is for high speed. Okay, now some properties of streamline flows are: streamline, tangent on streamline, tangent on streamline gives the direction of flow. Direction of flow or velocity. Got it? Then second property you can say, two streamline cannot cut each other. Cannot cut each other. Which means if they cut, let's say these streamlines are cutting at this point, so there will be a possibility of two tangents, which means the possibility of liquid to flow in two direction at same point. So it is not possible. It is impossible for a liquid to flow in two direction for a single point. It is impossible. So that is why the two streamline cannot cut each other. Any two. Okay. Okay. More denser the more density, or I will write more lines, more streamlines means more density. Okay. So if in this example you can say for this particular cross section and this particular cross section of same size, this is covering only three streamline, but this cross section is having 1 2 3 4 5 6. So flow will be denser this point at this point. So it is denser at this point and rarer at this point. Okay. So this is all about this streamline and turbulent flow. Turbulent flow is opposite to this. Okay. And it is achieved on very high speed. Now, the equation of continuity and Bernoulli's principle. This is a very important concept in fluid mechanics. So equation of continuity, firstly I will talk about this. The equation of continuity represents the conservation of mass. It represents conservation of mass. Okay, conservation of mass. So according to this equation of continuity, what it is say that for a incompressible fluid, if it is passing through a pipe of varying cross section, the fluid, or you can say the mass input or mass flow rate that is going inside this pipe will be same as the mass going outside the pipe. Which means that the rate of mass flow is always constant. So it can, you can say here that the rate of mass flow is constant, or volume rate, volume flow rate. Okay. So if this is a pipe of varying cross section, let's say the area here is A1, area here of this cross section is A2, and a liquid is passing into it with a velocity V1 at this point and leaving this with the velocity V2 at this point. So you can say the mass entering per second of the liquid will be same as the mass exiting per second. Okay, so mass flow rate is constant. That is why the mass will be conserved. Na? If the mass coming here, let's say per second is 10 kilogram, and if it is not leaving 10 kilogram here, so there will be the accumulation of charge inside it and the pipe will burst. So this is not going to happen if the fluid flow is steady. So for that also, the one point is also fluid flow is steady. Okay, or laminar or streamline. So this is valid for only the streamline flow. So you can say that from this point that A1 V1 is equals to A2 V2, or simply that AV is equals to a constant. This is the equation of continuity. Okay. Now, if I talk about the Bernoulli's principle, so as equation of continuity representing the conservation of mass, Bernoulli's equation represents the conservation of energy. Okay. So Bernoulli equation represents conservation of energy. As equation of continuity representing what? Equation of continuity represents the conservation of mass. So Bernoulli's principle represents conservation of energy. And what is that statement? You can write sum of for a streamline for a streamline flow of an incompressible fluid. This is important. Incompressible fluid, sum of all the energies possessed by the fluid per unit volume is constant. Okay. So this is the statement of Bernoulli's equation. So all the types of energy per unit volume of an incompressible fluid for a streamlined flow of incompressible fluid. So sum of all the energy possessed by that fluid per unit volume is constant. So we can say that if this is a pipe, you will consider this is at height h1, this is at height h2. Here the velocity is v1. At the exit, the velocity is v2. Here the pressure is p1. Here the pressure is p2. So we can say that p1 plus 1 by 2 times rho v1 square plus rho g h1 is equals to p2. I will explain what these terms are. P2 plus 1 by 2 times rho v2 square plus rho g h2. This is the Bernoulli's theorem, or you can say Bernoulli's principle. So in general, you can say it P plus 1 by 2 times rho V square plus rho GH is equals to a constant. So this is the statement of Bernoulli's principle. Sum of all the energy possessed by this fluid is equals to a constant. And this fluid must be an incompressible fluid. Okay. So this P is nothing but the pressure energy. You can say it is a pressure energy or pressure head. This 1 by 2 rho V1 V square is nothing but the kinetic energy or kinetic head of the fluid. And this rho GH is nothing but the potential energy. Potential energy or potential head. Limitation of Bernoulli's theorem are such that it is not applicable for a compressible fluid, because if the fluid is able to compress, there is a concept of elastic energy of that fluid, which will automatically disturb the equation that we have here, because we are not considering that fluid is compressible. If the fluid is compressible, so elastic energy of that fluid will also come into contrast. And also there is another limitation, that here we are not considering the viscous force or possessed by the fluid itself. Because of the viscosity of the fluid, there is a frictional loss. There is a loss of energy, and that we are not considering here. So this fluid we have considered a streamlined flow, smooth flow, and incompressible fluid. Okay, so these two limitations you will keep in your mind. Now, moving next, speed of efflux and Torricelli's law is the application of Bernoulli's theorem. So speed of efflux is such that this term efflux means outflow. Speed of outflow, which is if I have a container here and I made a hole here at this point, so the fluid will come out from this flow. That flow, that velocity of this flow is termed as the speed of efflux, or that speed by which the fluid will come out is termed as the speed of efflux. And this is the outflow of the liquid. Okay, flow. In this, we have two cases. First, when the, I will write it here, it is the speed of outflow. So in first case, when container is closed. So when container is closed, there is another situation. I will write the formula for it. Although you can derive it by the application of Bernoulli's theorem. You can take a point here at this point, take another point here and apply the Bernoulli's principle. You will get to know the speed. But we know it directly, so we are writing it here. So V is equals to square root of P minus P naught upon rho 2 into P minus P naught upon rho. Just a second. Plus 2G. Okay. So this is the speed of efflux. This here, the P is the pressure, or I will write it as P1 minus P2 so that you will understand it very better. This is P1, this is P2. This point is 1, this point is 2. So pressure of this point is, you have taken P1, pressure at this orifice or this hole, you will consider 2. Okay. So this is the, what say, the speed of efflux. And here we also have 2. So 2 by rho P2 minus P1 minus P2 is equal plus 2gh. If you can say that this hole is open to the atmosphere, so P2 you can also take in as P atmospheric. Okay. So finally this expression reduces to V is equals to 2 upon rho. Rho is the density of the fluid which is coming out. P1 minus P atmospheric plus 2gh. This is the actual formula for speed of efflux. Now, second case, when container is open. Container is open to the atmosphere. So if it is open to the atmosphere, this P1 point is also become as the open point. The water is coming out here. This point is here now. And this will also feel the same pressure as this point because these both are open to the atmosphere. So here this point 1 also become P atmospheric, and here we also have P atmospheric. So if you put the value of P1 as P atmospheric, so this term will vanish out. So V effective you will have here as square root of 2gh. And this is nothing but the Torricelli's law. Torricelli's law. Okay. Now, based on that, we have a question here. So here, consider a cylindrical tank of radius 1 meter is filled with water. The top surface of the water at 15 meter from the bottom of the cylinder. Okay. All information is given in the figure also. There is a hole on the water of cylinder at a height of 5 meter from the bottom. A force of 5 into 10 raised to the power 5 Newton is applied to the top surface of the water using a piston. The speed of efflux from the hole will be. Okay, so we know that speed of efflux will be square root of, because this surface is not open, this is closed, and an external force is applied to it. So the pressure is not same as the pressure of atmosphere. So we have to calculate it like P minus 2 upon rho P minus PA. PA is the P atmospheric plus 2gh. So h is given to us. What? H is the depth from the top surface. Okay. In this scenario also, this h is nothing but the depth from the top surface. Okay. So depth from the top surface is given to you as h is equals to 10 meter. G you also know. PA is already given to you. Now all the data you have to know, all the thing that you wish to know is this P. So we know that this P is equals to, on this piston atmospheric pressure is also acting plus this force is acting. This is a force, not the pressure. So we will write as PA plus F upon A. Now force ki value you have given. This is PA plus force is 5 into 10 raised to the power 5 Newton divided by area of this will become pi r square. Radius is given to as 1 meter, so it will be 5 by pi. So this pressure you will have as, just a second, I will calculate it. So this pressure you will have as 5 by pi. So it will become 1.6 and plus 1.01 10 raised to the power 5. So plus 1.59 10 raised to the power 5. So it will become 2.6 10 raised to the power 5 Newton per meter square, or you can say Pascal. Okay. So P we have calculated as 2.6 10 raised to the power 5 Pascal. Now we have all the data. We would wish to calculate 2 by rho P minus PA plus 2GH. Now 2 by rho, what is this? This is water. So if it is not given, you must remember it. The density of water is 1000 kilogram per meter cube. So you will put 1000 here. 2.6 minus again 1.01 10 raised to the power 5 plus 2 times 10 into 10. So this will become as, just a second, multiply with 2. Okay. So this will become 3.18 10 raised to the power 2, because this 3 power will cancel out 3 power, so 2 power will remain here, and this will become 2 into 10 raised to the power 2. So this will become square root of 5.18 into 10 raised to the power 2. 10 you can calculate outside, you can take it outside. 5.18 into 10. Now square root of 5.18 is equals to 2.27 into 10. This will become 22.7 meter per second. Okay, so this is the terminal, sorry, this is the speed of efflux. Now what we have did here, that we have calculated the atmospheric pressure also here. So this is the silly mistake that you can make. You can see that, okay, this the piston we have, so atmospheric pressure will also acting on it. No, we are applying the pressure on the piston. So we would only wish to consider this 5 into 10 raised to the power 5, not this PA. Okay. So if you make the correction, this will come out as 1.6. And finally, the pressure will be this, and you subtract it from this value. So finally, the expression that you will have as, the value of the speed you will have as 17.8 meter per second. So this is the silly mistake that you can make. So you do not make this mistake If the container is closed na, so take that P as the gauge pressure. Okay, do not consider the atmospheric pressure then. So here the velocity will be square root of 2 by rho, again P minus PA plus 2gh. So all the data you have know, 2 by 1000. P you have as what? 1.6 now. Okay, minus 1.01 multiply by 10 raised to the power 5 plus 2 into 10 into 10, and if you calculate it, it will come out as 17.8 meter per second. This is the speed of a flux that we have. So option C is the correct one. Now, Archimedes principle. Archimedes principle is very important principle, and the statement of Archimedes principle is that in a static fluid, in a static fluid, okay, the fluid must be static. The volume of solid inside the fluid, inside the fluid will be same as the volume of displaced liquid or displaced fluid. So when we put a solid in a liquid, here I am considering it to a liquid. So this is, let's say, liquid. So if I put a solid here, so that volume which is inside of the water will replaces the same amount of volume of water which is inside. So that is termed, called Archimedes principle. Okay. So here we have a term which is buoyant force. So buoyant force is applied by the liquid on solid which is inside it. So it is given by F is equals to density of the liquid multiply with volume of the solid immersed multiply with gravitational acceleration. Okay, now this is also termed as the upthrust. इसी को हम upthrust भी बोलते हैं. Okay, so we can say that weight, apparent weight, because when we put the solid inside the liquid, due to this buoyancy effect, the the solid will feel less heavy than it actually is. So what is the apparent weight that we feel inside the liquid? That weight is termed as the apparent weight, and which is given by actual weight minus upthrust. Okay. Now, based on that principle, we can say that first, if density of solid is greater than density of liquid, then it will sink in the liquid. वो डूब जाएगा. But in second case, if density of solid is less than or equals to density of liquid, then solid will float. Okay, so these are the two important conclusions you can capture in mind, and also the force of thrust force or F buoyant. Now, the viscosity and Stokes law. Okay, viscosity is the property of a liquid. Okay, and it is properties of fluid, I will say. So according to viscosity, the concept of viscosity is such that we know that the liquid or fluid will flow, or fluid flows in layers. And these layers, layer by layer, the liquid will flow. These layers will try to resist the another layer which is present just above the layer. Okay. So I've considered this is layer 1, this is layer 2. So this layer 1 will oppose the motion of layer 2. This layer 2 will oppose the motion of layer 3. And same thing will happen to all the layers. So these layers will oppose the motion of each and every layer. So they are trying to oppose the motion. Okay. And who is going to oppose the motion? Relative motion between them, the friction force. So due to which, due to the opposes the relative motion of layer. Okay. So layers opposes the relative motion of each other, due to which a frictional force arises in between them, and that frictional force is termed as the viscosity. So viscosity you can consider as the frictional force possessed by the different layers of fluid. Different layers of fluid. Okay. Now, this is defined as coefficient of viscosity is given by eta. Let me change the color. So coefficient of viscosity is defined by eta, which is equals to the ratio of shear stress to the strain rate, not strain itself, strain rate of change of strain, and which is given by F upon A divided by V, which is the velocity, upon L is the length. Okay. So eta, you can say that eta is nothing but FL over V into A is the area of cross section. The unit of it will be poise. Okay. This is the unit. Got it? Now, and this is called as coefficient of just a second. Okay. So this is called as coefficient of viscosity. Okay. Now, what is Stokes law? So Stokes law. Stokes law says that the viscous force applied by a liquid, or you can say a fluid, is given by F is equals to minus of 6 pi eta RV. Okay, so this is the Stokes law. Because if I consider this as a container, very long container, and there is a liquid fills inside it. We drop a solid sphere inside it. It will travel with a speed v. Initially, it is pulled by gravity. So the viscous force will act on this ball provided by this liquid. That viscous force is given by minus of 6 pi eta rv. So it is directly depending on this velocity, which means as the velocity increases, this force will increase. Okay. So after some time, what will happen? At this point, the buoyant force will acting in upward direction. Viscous force is also acting in upward direction. Now the magnitude of buoyant force is constant and the weight is acting downward. Weight is also constant. But this Fv is increasing with the speed. Initially, the weight, due to the weight dominating here, so speed will increase. As the speed increases, this Fv increases. So you can see here this Fv plus Fb is equals to mg. As Fv increases, this side of magnitude will increase, and after some time, it will equate the value of mg. And that particular time, there is no net external force on the body or on the sphere which is traveling inside the liquid. And at that stage, you can say that it is moving with a constant velocity or the maximum velocity it can attain. Okay. So that maximum velocity is called as the critical velocity or terminal velocity. So that velocity is termed as terminal slash critical velocity, which is given by Vt, which is given by 2 by 9 a square by eta rho minus sigma into g. Now where a is the radius of sphere, eta, you know, coefficient of viscosity, okay. Rho here is the density of solid, density of solid, and sigma here is the density of liquid. Right. So if you know all these values, put it inside the formula and get the answer. Now, based on that data, the terminal velocity, we have a question here. A raindrop with a radius r is equals to 0.2 mm falls from a cloud at a height h is equals to 2000 meter above the ground. Okay. Assume that the drop is spherical throughout its fall and the force of buoyancy may be neglected. Then the terminal speed attained by the raindrop. So buoyancy force you can neglect here. So terminal speed, we know that 2 by 9. Okay. 2 by 9 a square, which is a radius square, divided by eta rho minus sigma into g. This is the formula we have learned so in this. So all the data is given to you. A radius is given to you as capital R, 0.2 mm. Okay. Density of water is given. Density of air is given. Since in this question, water sphere or drop is traveling through a fluid which is air. So here the coefficient of viscosity of air will be considered. So here it is given in the question, coefficient of viscosity of air. Newton second per meter square. Same as boys. Density of air is also given to you. G is also, all the data is given to, just put and get the answer. 2 by 9. A square here is radius square, which is 0.2 mm. So you have to convert it into meter square divided by eta, which is 1.8, 10 raised to the power minus 5. Rho minus sigma is 1000, because here The material which is going through the fluid is liquid. So sigma rho minus sigma 1.2 into 10. Okay. So if you calculate this value nearly come across 4.94 meter per second. Option C is the correct option. How simple question is being asked if you just remember the formula. Okay. Now the surface tension and surface energy. What is surface tension? What is surface energy? So we will understand this concept by this example. Let's say this container is filled with a particular type of liquid only, and this is applicable for only liquid, and I will tell you the reason behind it. Okay. So if I consider two molecules, one is present at the surface, one is present inside it. So for inside present, this molecule which is present inside, all the molecules nearby it applying the intermolecular forces of attraction on it, so that it will remain in a stable equilibrium, because all the sum of all the forces on this particular atom or molecule is zero. So this will be in a stable equilibrium. But if you consider this sphere which is present at the surface, so downwise there is a force, but there is no force to compensate these forces in upward direction. So there will be a no force in upward direction. Got it? So if you see it on the top view and you consider imaginary lines, this is the molecule. So these are the forces on these molecules. So due to these forces, we know that when the stretching will be possible, when we apply the force in equal and opposite direction. The same thing is happening here. Okay. So due to which these unbalanced forces, this liquid film or the surface will be in a stretched condition. And if it is in a stretched condition, there must be a tension there. That tension is termed as the surface tension, which is given by surface tension. Surface tension is given by surface force, that is applied here, force per unit length. Okay. This length will vary according to the surfaces that you acquired. So in a case of liquid, you have only one free surface which is open to atmosphere. So here L is the length we have only taken. L is the diameter of it, you can say. Okay. Now, what is surface energy? So we will understand it by same concept. If you talk about this internal molecule which is present inside, so it is in stable equilibrium. So for stable equilibrium, the potential energy that it possesses, potential energy will be minimum. And minimum means negative. It has a negative potential energy. Okay. So if this molecule has a negative potential energy, let's say minus 100 joule, because it is in stable equilibrium. But if you talk about this molecule, this is present at the surface, and approximately half molecules are not present. Half forces are not present. So it is also in a equilibrium, but not stable. That stable as for the internal molecule, internally presented molecules. So we can say that it has a less negative value of potential energy, let's say minus 50 joule. So due to this difference of energy, there will be a net downward force on this molecule, because this molecule को निकालने के लिए we need less energy, and that is termed as heat of vaporization. So to protect this atom to go outside, this surface stretch itself in the downward direction so that it cannot go outside. because of this extra energy that it has. That energy is termed as the surface energy, because this energy is only possible because of the surface. If it is not present at the surface, it is present inside the liquid, it will not have the same energy. So this difference of energy is termed as the surface energy. Okay. Surface energy is given by surface energy is equals to surface tension, or you can say in terms of surface tension, surface tension equals to surface energy per unit area. Surface energy per unit area. More will be the surface area, more will be the surface energy. So that is why the liquid try to get a minimum surface area so that it will remain in a stable equilibrium on the surface also. So that is why liquid has a tendency to acquire minimum surface area. Okay. Now excess pressure in drops and bubble. This is the application of surface tension also. So for bubble, if I talk about, either it will be a liquid bubble or air bubble inside the liquid. So for bubble, excess pressure is Pi minus Po is given by 2S upon R. S is the surface tension of that liquid. R is the radius of the bubble. Okay. For this is for the bubble. Sorry, this is for drops. Drop, liquid drop or air bubble. Or air bubble inside the liquid. For soap bubble or any bubble which has two surfaces, because in soap bubble we have two free surface. How? If it is a soap bubble, one of the surface making contact with air here, and inside also this surface, the inside surface is also making contact with air. So we have two free surfaces here. We have two free surface. Okay. So for soap bubble, this is given by delta P, or excess pressure is given by 4S upon R. Okay. Now we will see it after this. So capillary rise, we have a capillary tube. Capillary means very, very thin. So when in a container of liquid, you put a very small tube, which is known as capillary tube. So liquid will rise inside it up to a certain point. Liquid rises into the capillary. Okay. That, let's say height is h. So this height up to which the liquid has risen in this tube, which is capillary tube, is given by h is equals to 2s cos theta divided by r rho into g. Okay. Where theta is the angle of contact. Theta here is the angle of contact. Okay. If I will share your information, if theta is equals to an acute angle, So liquid will be like this. Liquid will like this. This is liquid and this is the surface by which it is making an acute angle. So liquid will wet the surface. सरफेस और जो लिक्विड का मिनिसस होगा कैपिलरी में, इट विल बी लुक लाइक दिस और दिस. If theta is equals to a obtuse angle, the meniscus will be look like this, and liquid on any particular surface will be a proper droplet, and it will not wet the surface. Now the question: a mercury drop of radius 10 raised to the power minus 3 meter is broken into 125 equal size droplet. Surface tension of mercury is 0.45 Newton per meter. The gain in surface energy is. Now, this is asking for gain. So firstly, the radius is given to you as 10 raised to the power minus 3 meter. And this drop is broken into 1.5 equal sizes. Now the mass will remain same. And if the mass will remain same, you can say mass initial is equals to mass final. Mass you can write as density multiplied by volume initial, density multiplied by volume final. So it will same. So density will remain same. So volume initial is equals to volume final. Initially you have 4 by 3 pi r cube, and finally you have volume of 4 by 3 pi r final cube. Now this is for only one droplet out of this 125. So we have to multiply this by 125. Now this will cancel out. So r here is nothing but 5r final. R final you will have as r upon 5 or 0.2 10 raised to the power minus 3 meter. Okay. Now initial surface energy is given by surface energy initial is surface tension multiplied by area, and surface energy final is given by surface tension multiplied by area final. Now this is a drop, so it has only one free surface. So surface tension is also given to you. Now the change in surface energy is delta SE is given by surface energy final minus surface energy initial. So finally you will have as 125 droplet, or 4 pi r square is the area, r final, multiply with surface tension. Let's say it is 0.45. Okay. Minus initial, you will have a 4 pi r square, surface tension 0.45. Okay. Only this droplet you have. Now if you calculate this, you can take 4 pi as common, and 4 pi into 0.45 you can take common. It will become 125 into r final square, which is 0.0410 raised to the power minus 6 minus r square, which is 10 raised to the power minus 6. Okay. So if you calculate this, you will have a value of delta SE you will have a value of delta SE is equals to 2.26 10 raised to the power minus 5 joule. Okay, so this is it from my side. Yeah, this is it from my side. Any kind of problem you will have, you can make a query, and the next lecture will be on another topic. So this is it. Thank you so much for being attentive. And yes, keep studying, keep focusing, keep hardworking. Thank you so much.